Okay, so we're talking algebra, and today we're going to cover topics 1.8 to 1.11 in the course notes, so we'll go from page 15 to 25 today. As I said, the pace is fairly quick early on because we believe you've seen this stuff before and that we are just reminding you of what it is that you know, okay? So let's go. So we saw on Tuesday that if we have an algebraic expression, we can rearrange it in many ways. Sometimes it turns out to be simpler, sometimes it just looks to be equivalently difficult, but it can be rearranged. And today we're going to look at some more ways of rearranging, or more tools in our toolkit for rearranging expressions. And one of the things that we can use, and it's used a lot of course in arithmetic as well, is the idea of index notation. So index notation allows us to write expressions concisely. For example, instead of writing 2 times 2 times 2 times 2, we write that as 2 to the power 4. That's index notation. 2 to the power 4 is a much more concise way of writing 2 times 2 times 2 times 2. And of course, in this case, I can actually evaluate 2 to the power 4. When I do that multiplication, I get 16. So we can do the same in our algebraic expressions. If I have a times a times a times a, I can write that as a to the 4. And of course, that's much simpler. So we're going to make extensive use of index notation. Now, notice in our index notation that if I have 2 times 4 times 2 times 2, I could also, we could say that's 16 times 4 and hence get 64, but I could also say it's 2 times 2 times 2 times 2, there's 2 to the power 4, times 2 times 2, there's 2 to the power 2, and you can see here I've got 2 times itself 6 times, so I get 2 to the power 6. So clearly in here, that power, so I'll say here, note, 6 is equal to 4 plus 2. I've got 2 to the power 6 here because I had 4 of them there and 2 2's there. So to multiply two numbers with the same base, add the indices, is the arithmetic idea that we have here. So the same goes if we're doing this with algebra. I don't know what that number a is, but whatever it is, here's a to the power 4. That's a to the power 4. There is a squared. And as you can see, when I look at that, there's actually 6 of those. So that's a to the 6. So you can see a to the 4 times a squared is a to the 4 plus 2. So this property here is an example of an index law. It's a property of working with indices that holds no matter what number I choose. And it turns out that we in fact have 7 such laws of working with indices. And we will use all of these in rearranging our algebraic expressions. So in the end, you will in fact need to know these expressions, these laws. Now, once you've been doing this for a while and you think about it, you'll actually remember them all. But when you've got your L plates on, you probably won't remember them all. And I might remind you that in your mid-semester exam and your final exam, you're allowed a cheat sheet. And maybe that's a good thing to put on there if you can't remember them. Just an idea. So we have 7 index laws. Let's have a look at using those laws. Of course, If you look in your course notes, they're sitting in your course notes as well, but anyway, I'll put them all in the one spot. I think in your course notes they're spread out across the section, but anyway. So here we go. If I were to do this here, if I were to simplify 10x to the 6 times 5x cubed, then I can think of this. Now in here I've got, remember, because there's no sign in there, we think that's multiply. So that's 10 times x to the power 6 times 5 times x cubed. So every operation in there is multiply, and we know that when we multiply it doesn't matter which order you do things in. So I can actually write this as 10 times 5 times x to the 6 times x to the 3. Now, I can actually do that multiplication because I know what the numbers are. So I can go 10 times 5 is 50. And here are two numbers with the same base. I don't know what the base is. I'll call it x. And so to multiply two numbers with the same base, I add the indices according up here to law 1. And so in here this becomes x to the 6 plus 3, which is 9. And I'd say in there, look, I've used law 1 to do that. So here's a rather long expression. I want to try and simplify that. So sitting in here, again, remember your laws of arithmetic. What would you do with numbers in here? You always do your multiplication before you do your addition. So I'm going to do the multiplication first. Now in the multiplication, I can multiply the numbers 12 times 2 times 3. So that's 24 times 3, that'll be 72 in there, so that will be 72. Now, I have times a to the 7 and I have here times a squared. They are numbers with the same base. So I can add the indices in here. So this will be a to the 7 plus 2. And here are two numbers with the same base, s to the 5 and s cubed. So using my index laws, that'd be s to the 5 plus 3. And now I've done the multiplication, I can now add in that last number, which is a cubed. So far in there, all I've done is use law 1 up here. I've used that law up the top. Now that, of course, I can simplify. I can write that as 72a to the power 9 s to the power 8 plus a cubed. Notice I don't have an index law for adding numbers of the same base. That's because if I were to evaluate these things, I have to do the multiplication first, then I add them up. All right, so I can't do it all in one go. I have to do the multiplication, then I have to do the adding. So in here, with this algebraic expression, I just leave it like that. I can't simplify that any further. So I just leave that there. So that's law 1. Yes?
So there's no way you can split up the 8 to the 9 into 3 plus the 8 to the 3?
So the question is, can I do something with the 8 to the 9 here? Look, I can factorise this expression, but that's not necessarily simpler. Okay, so if I asked us to factorise, then we could do something with it. But for the minute, that's as good as we're going to do. Okay? We're going to talk about factorisation a little bit further down the track. Okay? Yep. All right. So now, let's have a look at law 2. And it says, if I divide two numbers with the same base, subtract the indices. So let's do that here. So here I might write this as 10x to the 6 divided by 5x cubed. If I write it like this, it's easier to see what's happening, I think. X to the 6th over 5x cubed. That's the same expression. And you can see in here that I could write that because we know how to work with fractions. I can do 10 divided by 5 first. Then I can do the x to the 6th divided by x cubed in there. We can actually do 10 divided by 5, that is 2. With the second term, they are numbers with the same base. So I subtract indices, and I have in there 6 minus 3. So I end up there with 2x cubed. And in here, in that little phase there, I use law number 2. I imagine once you get going, you can go straight from there to there without the lines in between. But perhaps while you're still sorting the laws out in your own mind, you might want to put the steps in. It's up to you. So in this one, again, you don't have to put this step in, but I will just to make it look more obvious. Because I have multiplications in the numerator and denominator, I can split that expression up that way. And now you can see that I'm working with numbers with the same base here, A and A, B and B there. So 27 divided by 9 is 3. A squared divided by A is A to the 2 minus 1, so that's A to the power 1. And if it's a power 1, we usually just don't bother to write that power. And finally, B cubed minus B, that's B to the 3 minus 1, so that is B squared. And again, I used law 2 sitting in there. Let me just slide back up and look at law 3 here for a bit. This one says A times B to the n is A to the n, B to the n. And let me just try to convince you that that seems reasonable. Imagine I had something like, so here as an example, 2 times 5 cubed. I know that that is 2 times 5 times 2 times 5 times 2 times 5. Right, that's 2 times 5 all cubed. Now I can do the multiplication in any order, so therefore I'm going to do the multiply the 2's together first, then I'm going to multiply together the 5's, and you can see here I have 2 cubed and I have 5 cubed. So that's 2 cubed times 5 cubed. So 2 times 5 to the power 3 is 2 to the 3 times 5 to the 3, which is what this law here is telling us. Okay? So that's law 3. Likewise, let's do something similar with this one here, law 4. Just say I had something like 2 squared all cubed. That would be 2 squared times 2 squared times 2 squared. That's 2 squared all cubed. Now in here, all of these numbers have the same base. So to multiply them, I add the indices. So that becomes 2 times 2 plus 2 plus 2. If I add 2 together 3 times, that's the same as saying 2 to the 3 times 2. So 2 to the 2 all to the power 3 is 2 to the 3 times 2, which is what that law there is saying. Okay, so we believe these things. They look like they're reasonable laws in there, and we're going to try and make use of those. I'll put that in there. Actually, I'll put it over here. So we're going to try and make use of those sitting in here. So a 10x to the 6 all squared, using law 3, that will become 10 squared times x to the 6th all squared. That's law number 3 that I used there. Now this one is x to the 6th all squared, so that becomes x to the 6 times 2, which is x to the 12th. So that was law 4 that I used there. In part B, I've got 3a squared b cubed on minus 2 all cubed. Now, in this case, this becomes 3a squared b cubed, all divided by minus 2 cubed. So essentially that's law 3. Law 3 says a times b in there. Well, I can guess my b here is 1 on minus 2, if you like. Or I could have added in another law and said a divided by b to the power n is a to the n on b to the n. They're essentially the same thing. So that's really law 3 sitting there. Now I can use law 4 in the numerator, and this becomes 3 cubed times a squared cubed times b cubed there. Now minus 2 all to the power 3 is minus 8. So in fact I've used law 3 again there. Law 3. And now I'll go 3 cubed is 27. I'll actually put the minus out the front. That's 27. A to the 2 times 3, b to the 3 times 3, all over 8. Again, depending upon your level of experience, you may not need to put all those intervening steps in, but I suggest to you that while you're still on your old plates, the more steps you put in, the better. Yeah?
Would it matter if you had negative 8 at the bottom instead of just putting negative?
No, I would accept that. That's having the negative down the bottom or whether it's out the front won't make any difference. It's the same number. Sitting over here, law 5, it says a to the power 0 is equal to 1. If how I had a look at this, if I said a to the m divided by a to the m, doesn't matter what m is, that's a to the m divided by a to the m, so that's a number divided by itself, that's definitely equal to 1. Agreed? Any number divided by itself is 1. Now, if my law up the top here, law number 1, well actually let's go law number 2. If law number 2 holds, it says a to the m divided by a to the m should be a to the m minus m. Now m minus m is 0. So for our index laws to be consistent, it makes sense that for a to the 0 should be 1. So that's law number 5. Using that law, here in A, I have 4 times 2 to the 0 plus 3 squared. Do the multiplication, that'll be 8 to the 0 plus 3 squared. 8 to the 0, anything to the power 0 is 1. 3 squared is 9, so that expression would simplify to just being 10.
So you're working out there, but you can just assume that anything with a 0 indices is just 1.
That's right, so I didn't even need to do the multiplication. I could have said number to the power 0 is 1.
No matter what's in brackets, it's just always.
Any number, so long as it's not 0, to the power 0 is 1. Yep. To a to the 0 minus b to the 0. We do our indices first, so that's 2 times 1 minus 1, so that comes out to be 1. You do indices before you do your multiplication in your order of precedence when you're evaluating arithmetic calculations. Big mass, I think, is the mnemonic, isn't it? Brackets, indices, then multiplication and division, then addition and subtraction. So in here I do the indices before I do the multiplication in there. If we have a look at law number 6 over here, if I have 1 divided by a to the n, I just said, look, 1 really, I could write that as a to the 0, and then via law 2, which we can just see up the top there, a to the 0 divided by a to the n should be a to the 0 minus n. 0 minus n is just minus n. So for our laws of indices to be consistent, we need to interpret a to the minus n as 1 over n. So there's law 6. And we will use it here to simplify these. So let's start off with a numeric example first. 2 to the minus 3 times 3 to the minus 2. So again, do our indices first. And 2 to the minus 3 we're going to interpret as 1 on 2 cubed. Multiplied by now 3 to the minus 2 we interpret as 1 on 3 squared. Now 2 cubed is 8. 3 squared is 9. And so I end up here with 1 on 72. So we're sitting in there, I used law 6 several times. Let's now have a go at an algebraic version rather than a numeric one. So part B says 2x to the minus 2 minus 2x to the minus 2. And the important thing in here is we have some brackets. And remember, in our order of operations, as I said, I think this is what we use to remember our order of operations in arithmetic. You do your brackets first, then your indices, then division and multiplication, then addition and subtraction. So they actually go together, those ones there. So in here, this is 2 times x, all to the minus 2. So this becomes 1 on 2x squared. Whereas in the second term, this is minus 2 times 1 on x squared. So you can see that the brackets make those two terms different. So now this becomes 2x all squared is 1 on 4x squared, and this becomes minus 2 on x squared. And so there's that one rearranged. Now in this case I could go a little bit further if I wanted to. I mean, certainly that expression and that expression are the same, but in here I could actually simplify, or I could rearrange this and put it over a common denominator. So let me do that. So in here I can actually go a little bit further and say, look, that's 1 on 4x squared, and this one will be minus 8 on 4x squared. To make the denominator here 4x squared, I had to multiply by 4, so therefore I had to multiply by 4 in the numerator as well. And 4 2s are 8. So I've put that over a common denominator, so I've got 1 on 4x squared minus 8 on 4x squared. So I could write that as minus 7 on 4x squared. In there. So all of those expressions represent the same number. If we are to look at the last law here, let me just give you a quick argument to say, look, this seems reasonable. If I said to you, what's the square root of a times the square root of a? Well, the square root of a number is a number that when it's multiplied by itself gives the number. So the square root of a times the square root of a must give a. Likewise, if I had a to the half times a to the half, according to our laws above, I would add the indices. That also gives a. So in other words, the square root of a must be interpreted in terms of our indices as a to the half. And that's what this is saying. A to the 1 on 2 is the square root of a to the 1 on 3 is the cube root of a, and so forth. So that also seems reasonable if our laws of indices are going to be consistent. I might put that one on top of that. Oops. Actually, that's the one I really want to keep because I want to keep those laws visible. Okay, so let's use that last law up here. And at this stage, I've only got a numerical example here. So let's do a. It says a 8 to the 1/3. We interpret that as the cubed root of 8. So what number, when you multiply it by itself 3 times, gives you 8? That turns out to be 2. Because 2 times 2 times 2 is 8. So that's law 7 in action there. Part B is a little bit more convoluted in that I've got 16 to the 3 on 2, not 1 on 2. So to simplify that, what we can do is we can split this 3 on 2 up. So I can write this as 16 to the half all cubed, because sitting over here, 16 to the half all cubed is 16 to the 3 times a half, 16 to the 3 on 2. So I've used law 4 backwards, if you like. I went from this side, I went from the right hand side to the left hand side. So I used law 4 backwards there. So let me just write that up here. Can you see it? Yep. Law 4 is what I used to get that. Now, 16 to the half is the square root of 16, all cubed. The square root of 16 is 4. 4 cubed is 64. So 16 to the 3 on 2, we can write as 64. Now, in here I split this up as a half times 3. I could have also split it up, so I'll put here or. If you'd wanted to, you could have said, look, this is 16 cubed all to the half. Should work. Now, 16 cubed, I believe, is 4,096 all to the half. And I believe that the square root of 4,096 is 64. So it won't matter which order you do it in, you'll get the same answer. Okay, so that's our laws of indices. They're all the ones that we should know and that will help us. So I'll stick those there. You can see they're going to be important. Let's see if we can use the laws of indices and our other tricks that we already looked at last lecture to simplify these horrific looking things here. So let's have a go. So part A. So I have 6x squared plus 4x cubed plus 2x to the fifth, all divided by 12x squared y. Now, sitting in here, in the numerator, well, first of all, if I were to evaluate this for a particular value of x, I would have to calculate x squared, multiply by 6, and then I have to calculate x cubed, multiply by 4, then I would add them, and I'd have to evaluate that entire top before I could divide by the denominator. So I can't just cancel out x squared and x squared, because this says do all of what's in the numerator before you do the division. Right? So as that sits, I can't do anything with it. But if you look in the numerator, you can see each of these terms has a 2 as a factor. And in fact, I can also see each term has x squared as a factor. So using my laws of indices, if I write 2x squared out the front, then what have I got to multiply 2x squared by to get 6x squared? 3. What have I got to multiply 2x squared to get 4x cubed? And the answer is 2x, because 2 times 2 is 4. X squared times x to the 1, 2 plus 1 is 3. So using my laws of indices. And lastly, what have I got to multiply 2x squared by to get 2x to the fifth? The answer is x cubed, because that x squared times x cubed is x to the fifth. So sitting in there, I've used my laws of indices, and I've also used the distributive law backwards. Okay? Now down the bottom, in the denominator, I would really like 2x squared to be a factor of there, and in fact I can write that as 2x squared times 6. Now I've got x squared times y, in fact, because the 2 times the 6 will give me the 12, the x squared y. So I can write 12x squared y as 2x squared times 6y. Now, if I were to evaluate that, it would say, calculate what's in the brackets, multiply it by this number, then divide by this number and this number. So I can cancel those out. Or alternatively, if you wanted to, you could write that as a separate fraction. Multiply by 2x squared, divide by 2x squared, so you're actually multiplying by 1. Whichever way you think of it. And so now here is my simplified expression, 3 plus 2x plus x cubed, all on 6y. Let's look at the denominator, part B. X plus y all squared plus a minus b x plus y all cubed, all over a minus b squared x plus y cubed. And there's a horrific looking expression. Can we simplify it? We can certainly rearrange it. One possibility might be to actually expand out all the brackets in the numerator and the denominator and see what happens. That's one possibility. However, in here we know we're going to use our laws of indices. And again, in the numerator, I'm going to recognise that x plus y squared is common to the first term and the second term. And if I do that, here I have x plus y all squared. That's a number. And what have I got to multiply it by to get x plus y all squared? The answer is just 1. And over here, to get a minus b times x plus y cubed, I'll have to go a minus b, and this was just x plus y to the power 1. X plus y squared times x plus y to the power 1 gives me x plus y cubed in there. So again, I've used my laws of indices and the distributive law backwards in there. Now in the denominator, I would really like to be able to see an x plus y squared. And what have I got to do? If I then multiply that by a minus b and another x plus y. So I've multiplied by x plus y squared, I've divided by x plus y squared, so they cancel out nicely. And so I'm left with 1 a minus b x plus y all over a minus b x plus y. Oops, there must be a squared in there somewhere. I've left that out. There we go, squared. And once again, you can't cancel out the a minus b's here because to evaluate this, I would have to calculate that term, a minus b, the x plus y, then I would have to add 1 before I do this division. Alright, so I'm not multiplying by a minus b and then dividing by a minus b because I've got to add 1 first. So that's as far as I can go. So can't simplify further. Even though you would like to, no can do.